In this skill, we're going to be converting between change in Gibbs free energy and equilibrium constant for a given reaction. In this question, we're predicting the equilibrium constant K for a fictional reaction involving fictional elements with the symbols G, R, A, and M at a temperature of 1310 Kelvin. So here's our reaction that we're going to be figuring out the equilibrium constant for. We've been given the delta G naught, the change in Gibbs free energy for the reaction, as 44.5 kilojoules per mole. Let's head to our reference sheet. Here's our equation that relates Gibbs free energy and the equilibrium constant. Delta G naught is the change in Gibbs free energy. R is the molar gas constant, which is given down here as 8.31 joules per mole Kelvin. T is the temperature that must be measured in Kelvin, and K is our equilibrium constant. So there's our equation, and we know that R, the molar gas constant, is 8.31 joules per mole Kelvin. So we can go ahead and fill in R here. We know it's 8.31 joules per mole Kelvin. We also know the temperature is 1310 Kelvin. The Gibbs free energy we've also been given, but we've been given that in units of kilojoules per mole. However, because R is given in units of joules per mole Kelvin, we're going to have to convert our Gibbs free energy change into joules per mole instead of kilojoules per mole. And remember, kilo means 1,000. So 1 kilojoule is 1,000 joules. So let's set up our dimensional analysis table. We want kilojoules to cancel out, so we're going to put that on the bottom. We want joules, so that's going to go on the top. And we have 1 kilojoule is equal to 1,000 joules. So now we'll multiply everything on the top, multiply everything on the bottom, and divide the top by the bottom. So the kilojoules is going to cancel out, and we're left with 44.5 multiplied by 1,000 divided by 1 joules per mole. So if we put that into a calculator, we're going to get 44,500 joules per mole. So let's go and fill that in now. Awesome. So we've got 3 known variables. We've got 1 unknown, which is K. Here's our equation relating Gibbs free energy and K, the equilibrium constant. We're going to have to rearrange this to get K on its own. So right now I've got negative RT multiplied by ln K. So I'm going to divide by negative RT on both sides of my equation so that the negative RT will cancel out on the right. That leaves me with delta G naught divided by negative RT is equal to ln K. Now, to get rid of ln, I need to use the inverse function of ln, which is e to the power of. So if we do e to the power of delta G naught over negative RT, that's going to be equal to e to the power of ln K. And e to the power of and ln are inverse functions, so they cancel out. So we're going to end up with K is equal to e to the power of negative delta G naught divided by RT. So let's go ahead and put our numbers in. E to the power of negative delta G naught was 44,500 divided by R, the molar gas constant, which was 8.31, multiplied by T, which was 1310 Kelvin. So if we put that into our calculator, we get 0.0168 for our equilibrium constant K. Let's go ahead and fill that in. So what is the equilibrium constant K for this reaction? We've just calculated that. It's 0.0168. Okay, so now I need to think about what this means. Now our delta G value was positive. That means delta G naught is greater than 0, and that means our reaction is unfavorable in the forwards direction. So is our reaction thermodynamically favorable? No, it's unfavorable. So if our delta G is greater than 0, we know that means our K has got to be less than 1. And that's exactly what we calculated here. We found K was 0.0168. That's less than 1. So if K is less than 1, that means the backwards reaction is favored. And that means that our reactants are favored at equilibrium. So we can go ahead and fill that in here. Our reactants are favored at equilibrium. So in this question, where we're using Gibbs free energy to find the equilibrium constant K, or using the equilibrium constant K to find the change in Gibbs free energy, we're going to be using this equation here. Make sure that your Gibbs free energy is in units of joules to be used in this equation. So you might need to use the conversion between kilojoules and joules. Once you've found both the change in Gibbs free energy for the reaction and the equilibrium constant, we can use those to figure out what's happening in our reaction. If the Gibbs free energy change is greater than 0, we have an unfavorable reaction, meaning that our reactants are favored at equilibrium and K is less than 1. If our delta G naught is less than 0, that means we have a favorable reaction in the forwards direction, meaning our K is greater than 1 and our products are favored at equilibrium.